The Dirac Delta function, Dr. Phys Theoretical Physics. Dirac here defines for us delta of x to be 0 for x everywhere except x equals 0. And then when x equals 0, there's a point at infinity. Wow, a discontinuity at x equals 0. What is this? And then you're trying to tell us that the area under this graph, what graph? There's just a point there at x equals 0. You're trying to tell me the area is 1? Wow, doesn't make sense here, but we're going to clean this up mathematically as we go in this chapter. But for now, just take this crazy definition. Just take that as a given and see what we can get out of that. We're going to look at the box function to understand better what's going on, and the box function here, given by this red graph. Ignore the blue graph f of x for now. We'll need that in a second. This red graph, the box function, is centered on x equals 0, and it has a width of delta and a height of 1 over delta. So the area of this box is the height times the width, which is 1 over delta for the height times the width delta, and that gives 1. This is a family of box functions, and when we let delta go to 0, we get thinner and taller, thinner and taller, thinner, thinner, taller, taller, and we approach here Dirac's idea of a infinitesimally thin box, actually no thickness, and that point way up there at infinity. Well, there's a nice property here called the sifting property of the Dirac Delta function, and we will see that by considering the blue graph here, f of x, and the box function. Before we do that, though, let's just focus on this little strip in here, this little area under the function f of x. Now, the area here can be given by some average value of the height here, times delta. This is known as the mean value theorem for integration, that there is one value in here you can find at x equal to c, and the height will be f of c, and that height times delta gives the area of that strip. Okay, now we're ready to do the product of the two functions. The box function times the function f of x will give nothing to the left and to the right of the box, where the box function is 0. And here we'll simply have this height f of c, some magic height in there, times the 1 over delta for the product, and multiplied by our thickness delta, and via the mean value theorem we have this nice arrangement where the deltas will cancel and you'll get the function evaluated at x equals c. Then when we let delta go to 0, we will squeeze f of c to be f of 0. And when we take that limit, the box function becomes the delta function, and we have this nice result that when you multiply the delta function with another function f of x and integrate, you sift out, you pull out f of 0. In the more general case, if you have the delta function where the argument is x minus a, then you sift out f of a. You can show this by letting z equals x minus a. Do your change of variables here, and then write this situation here with z's. So you have delta z, f of z, dz is f of 0, and then use that with the change of variables, and you can get this nice result.